Welcome, my dear students, for new linear algebra course. This I am Nadimur Rahman, professor in the Department of Mathematics at Aligarh Muslim University, Aligarh. Over the next 12 weeks, we discuss together with the basic linear algebra. This is a course for important course for any undergraduate level. In this course, we start with the basic vectors and then vector spaces. Also, we have to discuss about the linear transformations, matrices of a transformation. In the end, we have some applications of eigenvalues, eigenvectors, and eigenspaces is there. This linear algebra has a wide applications, and this course is a modern important for modern science and technology. So let's begin with the natural questions. Why study linear algebra? That means why we have to study the linear algebra. So linear algebra is just not just a course, but a way of thinking, a language of modern science and technology. Why we say that is a language of a modern science and technology? That means this subject has a wide applications in the different branches of a science and technology. One way we start with the basic about the engineering. In engineering, this linear algebra helps solve the system of linear equations for circuit designs and structural analysis. In computer graphics is also used, its power imaging rotations and 3D animations we have to using this linear algebra. In data science and artificial intelligence is lies behind the machine learning algorithm, deep neural networks and a big data analysis we have to using this thing. Also, we use this linear algebra in the coding theory and cryptography. We have to use all the linear codes. It's very important linear code for the this barcodes and all these things we have to using in day-to-day lives. Books, ISBN codes. Then we have to using this linear algebra for coding theory and cryptography also. Also, we use applications in physics and the quantum mechanics is there. So that's why we have to study this linear algebra has various applications in the different branches of the science and engineering. Not only this, we have to some other applications for eigenvalues and eigenvectors. We can find out the possibility solutions. So let's begin because linear algebra is we have to some algebra and linearity conditions are there. We start the very basic things for our subject is a operation. So we start as a binary operation. So means we say that binary operation is simply we can say that we have any non-empty set. For example, we have a is any non-empty set. We have any function from a cross a2 we have to define as a, and then you can say that is clearly this element of this is a and b. There for every a and b are the element of a, and then this map for a unique elements of this over f of ab into this form. So this means this is the elements of this image also belongs to the this set a is there. So in this case, suppose this is operation of this, we have to just say, for example, if we take we define this f of ab in the form of this a plus b, then we can say that this addition is a operation and that operation is this. So we have to simply say that under addition, we have to define a set of, for example, real number, close real number, to we have a real number. So we take any two real numbers, we have to take any two elements from the set of a real number. For example, we have a and b are the two real numbers which is belongs to the this, because the elements of a r cross r is a ordered tuples is there, and this form is there. And then because we have a operation, we have to taking the addition, so we take a plus b. Simply is this means we can say that in the form a and b are the ordered pair there, because a and b are the real numbers when we take a sum of these two real numbers, this is again is a real number. That means we have a, this is a unique number we have to produce this thing. So that's why we can say that in this case we have a, the operation is simply, this means is a function, and this should be a well-defined function where is satisfy, this means there is exist a unique element in this. And also there is a second thing is there, this under this operation, whatever this element operate into this operation, this should be belong to the produce a unique element into the set of this real number. For example, if we take a multiplication as a binary operation, then we can say that again we have to set of real number to real number, we have to take a map from R to R. Again we have to take any element of A and B, and that is maps to A into B types, because this is A and B are the real number. If we take any two real numbers, again you product take a product of these two real numbers, this must be again is a real numbers. So this means we can say into this form, this simple way we can say that binary operation means we have any functions, a non-empty set x with a function from a cross s to s. So what the formal definition of this binary operation, we can say that let us be a set, a binary operation on s is a function, this star we have denoting as a operation of this. You can not a star, you can use any other O also, they can using some notation is there. So this is simply is a notation we have to using the operation star, we can take as accordingly our definition. So binary operation on a set is a function, this s cross s to s, where elements of A and B are the element of S, produced a unique element under this operation giving the S is there. So this means all ordered pairs of A, C, B element in S and into produce a element into a this again the elements of S in this form. So this way we can define it. Now we have the word is a binary is here. Binary is simply means say that we have to just say that simply indicate that the operation take into two elements of a S and splits out say a new element. We can take a binary means we take a two elements and splits out this new element in this form. For example, if you take a set of integer under addition, if we have a then we have a this form into map from to z to z. I take a, for example 2 and 3, and then this is map 2 plus 3 is equal to 5, that is the unique element, this is split out. So we take a two elements of this is splits out as a new element that is the 5, and this means we binary operations we use binary is simply indicate that the operation take into two elements of S and split out a new elements. Now this binary operation is understood by the two important things is there. You can just say that we have to check in this form. We have a function that is a function is well defined, the operation is well defined, means given A and B belongs to the S, there is exactly one element of a C such that this operation is equal to the element of this. So that means we can simply say that whatever function we have to taking f, this operation from set non-empty set cross this to this is a well defined, and also because we can say that this new element C is belongs to the also belong to the this set S. That means we can simply say that this should be the closed under this operation. So that means we can say that S should be closed under the whatever binary operations we have. That means closed under this operation means we take any two different elements of this element of this S, and under this operation produce a new element. This element is also belongs to the set of a S is there. So that means we can simply say that is a binary operation. Now we have to by definitions, now we discuss some examples of a binary operation. Very trivial examples under we take a, for example, I take a set of natural number. We take a set of natural number, and then we have to under addition, then set of natural number. Under addition we have to define into this form cross set of natural number to set of natural number. Then if you take a clearly take any two elements of a set of natural number, if we take x and y are the two elements of a set of natural number, then under addition we have to x plus y is also belongs to the n, is clearly this thing, because sum of a two natural number is again produce a natural number. So that means we can say that under addition set of natural number is a binary operation. Again, we can say that under multiplication, for example, set of natural number, if we define set of natural number under multiplication, so we can take n cross n to n. Then again, if you take any two elements, x and y belongs to the set of natural number. If we take a x into y, the product of a two natural number is again is a natural number. That means this again produced a unique element in this thing. So this means this satisfy, this is well defined, and also from this condition is a closeness also there. So we can say that this means set of natural number under this addition and multiplication is a binary operation. Similarly, we can say that set of complex number under addition to is a binary operation. Why this is set of under addition is also is a binary operation? We can simply say that if you take any two complex number, z1 and z2 are the two complex number, then if we take a sum of a two complex number is again is a complex number. That means we can say that is a well defined also, and there is a close also, that means both the properties of a binary operations are hold here. So that means we can say that under addition of a two complex number, and similarly you can say that under multiplication of a two complex number we have a, this means if we have taken again z1 z2 are the complex number, then z1 into z2 is also the element of a seized. So this means we can say simply say that the under of addition and under multiplication set of complex number is again is a binary operation. Similarly, we can define for a set of integer, set of rational number and set of real number, all are the examples of a binary operation under the addition and multiplication. Now we have to take a matrix we go to the matrix, we take a n by n. I take for example take a 2 by 2 matrix, 1 2 by 2 matrix. There is elements of this, suppose m2, and elements of this r is the form of this a b c d, such that a b c d are the element of r. And now we just said that we define a under addition of a matrix addition m2 r cross m2r to m2r. That means we take a two different matrix and then because the element of a and b are the this thing, so we take a matrix. One matrix is the form of a b, a1 b1 c1 d1, and we take a b is the element of a2 b2 c2 d2, where we can say that a1 b1 c1 d1 and a2 b2 c2 d2, these are the elements of the integer. Is a r from real number. Now we take a plus b. A plus b, simply we can say that we have to adding component wise, that means a into this, b into this, c into this, and t into this. So this means we can say that a1 plus a2, b1 plus b2, c1 plus c2, d1 plus d2. Now because a1 and a2 both are the real number, then this means we can say that a1 plus a2 is also is a real number, because a1 and a2 are the real number. Similarly, we can say that this b1 b2 are the real number, then sum of real number is again is real number. That means this is all the elements are the belongs to the R. So this means this completely matrix belongs to the M2R. Means we have a addition of these two matrix. We can say that simply in the form of this we add matrix addition and matrix multiplication is again is a set over the set of a real number is a binary operation. If we take a set of under addition set of integer is again is a over the in place of a r, if we take a z, under addition is again is a binary operation. Similarly, in the similar manner, we can define the binary operations under multiplication. We take a and b, and now we have to take a multiplication of these two matrices, and because if we have a multiplied by the element component wise row and columns, so again produce the elements of a product under matrix is again is a real number, because product and sum of the two real product of a true real number a real number, and if we add a real number is again is a real number. So in this case we can say that this example is this. I just slightly change this example. In place of a n by n matrices, if suppose we take a invertible matrices, so invertible matrices means we can just is a determinant is not equal to 0. So we take a two invertible matrices and the coefficient is defined into this form. Is this is a binary operation or not? That's the question. Now we think about, because we have to taking this invertible matrix. So we again take for example n is equal to 2. We try to explore what the possibility of a 2 by 2 matrices under binary operation is addition. We have to taking in the form of this thing. So we take n is equal to 2 means we have take any 2 by 2 matrices where invertible matrices means determinant of this matrix should be not equal to 0. So we just try, for example, if we take a I take a 1 0 0 1, and then b I take is the form of a minus 1 0 0 minus 1. Now clearly this a is invertible because the determinant is not equal to 0. So this is the belongs to the, you have a m2 over r, and again this is we have again this set is the element of a, this is also the element of a m2 r. So this means clearly these two element we have to choosing, this is the belongs to the this matrix we have a m2r. So m2r we have to taking the form of this already is a collection of all invertible matrices. So now we take what is possibility of a plus b, that a plus b is equal to 1 0 0 1 plus minus 1 0 0 minus 1. And now we know that the property of this, so 1 plus minus 1 and 0 plus 0, 0 plus 0 and 1 plus minus 1, because these are the real numbers. So this means this can be in the form of a 0 0 0 0, and this is clearly 0 0 0 is the determinant is a 0 matrix, and 0 matrix is not an invertible matrix. So is not invertible matrix, that means this does not belong to the m2 r. That means we clearly say that this is a binary operation, is a defined but is not a closed. So this is clearly is not a binary operation. Why is not a binary operation? Under addition, set of invertible matrices under addition is produce a element of a 0 0 0. In general, we can say that if we have a matrix A is there, A is the element of a m and r, then we can say that minus a is also the element of a m and r. So this means we can say that a plus minus a is giving a 0 matrix. So 0 matrix is giving this is 0 matrix does not belong to the m and r. So in place of in general we can say that we take any element of a of a this which is invertible, and then minus a also is invertible. So then we can say that if we add these two matrices, then clearly we can say that sum is again is 0, and that means 0 is not a invertible matrix. If 0 is not invertible matrix, means this does not belong to the our set Mn. So that means we can say that this Mn is not closed under the matrix addition. So this means is not closed under matrix addition, is not a binary operation. So this is not a binary operation. In general, we can say that is clearly is not an invertible. Now I just take some subtraction is not a binary operation in the set of integer is very trivial example. If we take a 2 and 3 are the element of a set of positive integers, and now if we take a subtraction 2 minus 3 is equal to minus 1, clearly is not a positive integer. This does not belongs to the set of positive integer, that means the subtraction is also is not a binary operation on the set of integer, but subtraction is a binary operation on the set of integers, but not positive integer. If we take any two integers and then we have to take a subtract of a two integer, is again giving the some integers are there. So in the subtraction under addition, subtraction is a binary operation on the z, but subtraction is not a binary operation on the set of a positive integer. Now we have to take some different types of example for a binary operation. That different type of examples we can say that in the form of a this form, in the form of a define, if we define AP is the element R, so this means binary operation if we have to take set of real number to a real number, and then we take A and B are the element. A star B is the type of A and B. Is not a binary operation. Why? Because B, if we take B is equal to 0, so this is B is equal to 0 means this operation function is not a defined. So it is not a well defined. That means we can say that if it is not well defined, we simply say that is not a binary operation. So now again as one more example I will discuss in this form because undefined whenever B is equal to 0. Now if we have this again we take a binary operation for set of real number to set of real numbers, and then we have to define A star B is the form of A plus is equal to C. This is the element of a C. Now C we have to restriction C is a some number larger than F is. This means C should be greater than of A plus B is there. So whatever this is larger than A plus B. So this is again we can that is not a we cannot find as a unique element in this case. For example, if we take a 2 and 5 is the element of a this is the element of a R cross R, and then we can operation is this means we can the C can be calculated in the form of a 2 plus 5 is equal to we have a 7. That means C should be the larger than 7. So C should be the larger than 7 means you have a 8, 9, 10, but this is all the 6 number is going on, and in this case we can say that we can simply say that this is not a unique element we cannot find. So this means it's not a well defined. If it is not well defined, then clearly exactly why not well defined? Because there is not a unique element. So it is not not clear exactly what A star B should be is there. So now I think I have explained you about the about the binary operations. So we move further for explaining you the next things is a very important portion when we define is a vector space. So we have a need a field. Field means we have a working in the binary operations. So we have a in field we have a two two binary operations. One is addition and another is a multiplication. So that means we can say that if we have a when we define a field, if we have a F should be a, we can say that clearly the non-empty set, and then we have a we equipped with a two binary operation means F cross F2 F means under addition this should be the closed, and also there is another operation binary operation is F cross F2 F. So that means that is a if we have to just say that F non-empty set with binary operation is addition and multiplication is satisfied certain axioms of the things, we can just say that is called is a field. So that means a non-empty set F with the two binary operation, I just say that S star addition, we can lambda and mu are this is lambda plus mu, and where lambda and mu are the element of this field, and multiplication we denote it by dot. Again the lambda dot mu is there. Is this non-empty set with this two binary operations is called a field if it satisfies certain properties. First is this should be a under addition should be a closed. So that means under addition should be a closed means if we take a and B are the element of a field F. So if we take a same element, if we take a lambda and mu are the element of this field F, then under addition lambda plus mu should also be the element of F. So this means we can say that this under addition should be closed. Next we can say that under addition it should be the associative. So we take a lambda, mu and nu are the elements of some F. So we have to say that lambda plus mu plus nu is the same as a lambda plus mu plus nu for all lambda, mu, nu are the element of a field F. This in this case we can say that this satisfies this associative conditions, also satisfy the commutativity. This means lambda and mu are the element of a field F. Then lambda plus mu is the same as a mu plus lambda, and also this satisfies the commutativity condition under addition. And also there exists an element 0 belongs to the F such that lambda plus 0 is equal to lambda is equal to the 0 plus lambda for all lambda is the element of F, and this is called the existence of a identity, and this 0 is called the additive identity of that set. Means in this case we have to find a certain element in the set which can adding to the any element of this set, giving the element itself is there. Also for every lambda belongs to the F, there exists some minus lambda also belong to the F such that lambda plus minus lambda is equal to giving the identity element, additive identity is 0, and that is equal to again satisfy this condition. For every, this means for every lambda we can find a minus lambda in this also set in the field F, and we take a lambda plus minus lambda as equal to giving the identity element. If under addition, if it satisfy these properties, and we have to furthermore, so we have a two binary operation addition. So F under addition satisfy these properties. Means first is under addition should be the closed, second under addition is associative, under addition is commutative, under addition existence of identity, and also existence of inverse is there. Now we move to the next is about the under multiplication. What is the possibility of under multiplication? So we have a multiplication which we have again from F cross F to F. That means we take any two element lambda and mu is the element of F. This should be implies that lambda into mu is also belongs to F. That means under multiplication this should be a closed, and also under multiplication this should be the associative. So lambda mu nu are the element of F. This implies that we have to lambda plus mu and then plus nu is equal to lambda times plus mu plus nu. Under addition, under multiplication should be closed, under multiplication should be the associative, also under multiplication should be the commutative. This is lambda plus lambda into lambda multiplied by mu should be the mu into lambda. So this means we can say that this property also there exists a 1 belongs to the F such that we have a 1 into lambda is equal to lambda into 1, and 1 is called is the this call is the multiplicative identity of this. And also we have to any take any non-zero element lambda belongs to the F. There exists 1 upon lambda also belongs to the F such that lambda into 1 upon lambda is equal to identity, and then we can say that 1 upon lambda into we have to lambda. So this means its multiplicative identity also satisfies. In this case under multiplication it satisfies these conditions. So we can say that into this form. And also we have one more is satisfy the both the distributive property over addition and over multiplications, when we take a for all lambda, mu and nu are the element of a field, the lambda into uh, addition under binary operation under addition, mu plus nu is satisfy this condition, and we have to reverse is adding this, let this satisfy. So if we can say that this f under addition and multiplication, if satisfied these 9 properties, we can say actually not 9, 11 properties, when we have to say that under addition and multiplication is a close also. So we can say that if any set which satisfy these conditions, we say this set is called is a field. Very trivial example of a field is set of real number. Why is set of real number? Because we know that under addition we have a r cross r to r. Now we know that if we take any two real number, we have to take suppose we take a x, y and z are the real number, then we take a x plus y is also the real number. That means it is a closed under the addition. Similarly, we can say that if we have to x, y, z in the element, so we have to, if x plus y is a real number, and if we adding this is because we have a x plus y plus z for all x, y, z belongs to the R, because set of real number is always associative, and also set of real number, if we take x plus y is the same as a y plus x for every x and y is there. Also you know that 0 is the element of this set of R. If adding this 0 plus x, we have a giving x is equal to x plus 0. So this means this element is clearly, and if x is the element of a R, we know that minus x is also belong to the R, then we have a x plus minus x is giving you a some these two real numbers is giving the 0 real number, then we can say that minus x plus x. So this means under addition is satisfy all the properties of the field. Similarly, we can say that is satisfied under the multiplication of R. We have to commutative multiplication of a real number is closed, this also associative, and then 1 is the element of a set of real number, and now we have to multiply by 1 into the any number x, this is giving the x itself, so x into 1, that means 1 is the multiplicative identity. Also if x is the element of a R, then 1 upon x is also the element of a R. That means we can say that x into 1 upon x is equal to giving the identity, and this is equal to 1 upon x into x. So that means clearly multiplicative identity is also exist here. So this means this set of real number under addition and multiplication is clearly is a field. This is very important field for our course. We have to most of the time our course we have to concentrate on the R is a field. So this I just said that what we have to prove is under addition is closed, under addition associative, and identity element 0 is the additive identity. For each non-zero element has a inverse. If A is the element, minus A is also, and commutativity condition is also satisfied, and also this product of a two real number is a real number, so is closed under the multiplication. Also real numbers are associative, also 1 is exists there, so 0 is not element of a, 1 upon a is the element of a is this thing, and under multiplication of a real number is a commutative, and also satisfy the distributive properties are there. So this means R under addition and multiplication is a field. Similarly, we can say that set of a complex number under addition and multiplication is a field in the similar fashion, because we take a sum of a two complex number is again is a complex number, and if we have multiplied a complex number is again is a complex number, and we have satisfied the associativity, commutativity. If is the 0 is the 0 plus I times 0, this is the element of a C. If we take a x plus iy plus 0 plus I0 is giving you a x plus iy. So 0 plus I0 is the additive identity of there, and x plus iy is the element of a C, then minus x I times minus y is also the element of a C, and this is the inverse of a this element. So in the all the properties automatically satisfy into this form. So we can say that this set is a clearly is a set of a complex number under addition and multiplication is a field. A set of rational number is again similar fashion. Now what about the set of integer? This is not a field, but a set of integer you can see under addition satisfy all the properties. All the and set of under addition is a closed. Set of under addition integer under addition is associative. Set of integer under addition is commutative. 0 belong to the z. Additive identity are there. Every element has a inverse are there, and then we have to go to the multiplication. If we take a under multiplication is a closed, under multiplication is associative, under multiplication is a commutative, and you have a 1 is also belong to the element of a z, and then 1 into x is equal to, you have a x is equal to x into 1, means additive multiplicative identity also x into the z. But you say that if we have a x is the element of a z, but there does not exist 1 upon x, does not belongs to the z. So this means every non-zero element we have a multiplicative inverse, but if we have a 2 is the element of a z, but 1 upon 2 does not belong to the z. So we cannot find a inverse of every non-zero element in the set of integers. That means set of integers is not a field under the binary operation addition and multiplication. Now I have to stop today's lectures here, and this is the basic things about which are we have to need into the next lectures, because I just say that the field is very important. Before field we need a binary operation, so that's why binary operations related to the field. Now we have to move to the next lecture. We have to discuss about the definition of a vector space and some examples and other things. Thank you very much.